This lesson is on section 1.6 from our text on trigonometric functions. First, I want to talk to you about something called a radian. A radian is just a measure of arc length, really. One radian has the length of one radius. That's it. Arc length. We're talking about circles here. So if I draw you a circle, and I take this length we call the radius, and I just stretch it around the edge of a circle to get an arc length. Okay, this is also one radius. The angle that is included in that arc length it cuts out one radius around the circle, if you will. We call that angle 1 radian. So a radian is a measure of arc length for angles within a circle. A radian just has a length of 1 radius. There's nothing more complicated than that. And a nice fact about circles is that all circles have the exact same number of radiuses, right? Radians in their angles, in their total circumference, if you will. How many? 2 pi radians. Okay, this is the formula for circumference. 2 pi r. 2 pi radiuses, right? If we remember, multiplication is just this idea of counting up how many of these things we've got. So if you take 2 pi radiuses and you add them all up, you've got yourself the circumference of the circle, no matter what this radius is. So the entire circumference is always 2 pi times the radius. So that tells you exactly how many radians in arc length there are around a circle. And that makes this an intrinsic definition to angle. We're defining angles with radians in terms of the very circle that they come from. So this is quite different from degrees because degrees are sort of an arbitrary decision of we're gonna cut a circle's total circumference into 360 pieces, and those 360 pieces will each call degrees, and they probably for sure are, based upon some unit of measure around the earth or some time measure for traveling around the earth, but they're not intrinsic to the very object that you're measuring, not like radians are, because they come right from that circle that we've got. Hey, Noah. You eating some Cheerios, buddy?
No.
Yeah, okay. Can you go find Mommy for me?
No.
Thank you, bye.
Mom.
Okay, come on. We gotta go. Okay, go find Mommy. All right. At least now he's outside the door. All right. Where were we? Okay. So this actually gives us a nice way of finding arc length in total. So this is the first example. This is something you can't do with degrees. Degrees require a conversion require conversion to radians actually prior to this sort of thing. So we want to find the length of an arc subtended on a circle of radius 3 by a central angle of measure 2 pi over 3. So we've got a question where the radius of a circle is 3. To make the other Mr. Love happy, we'll say 3 centimeters. And we've got the angle, theta is 2 pi over 3. This is in radians, not in degrees, so this is nice. And the question is how long is the arc length in this angle? And if you remember just the definition of radian, this is trivial because the angle, theta, is literally the number of radiuses. If you want to know how long around the circle this arc length is, all right, so we take pi here. That's half the circle. We split it into thirds, and we've got 2 pi, or 2/3 of that. This is the angle we're talking about. We're looking for this arc length. Okay, if you remember exactly what this is, 2 pi over 3, it's the number of radii that fit in here. If you know how many of something fit somewhere, and you know how big each of them are, you simply just multiply, right? This is the number of radii times the length of one radius, and that's this arc length S. This is just a trivial problem when you're thinking about angles of radii, right? You have to count how many there are, and you multiply by their length, and you've got the total arc length. Okay, and that gives us a general formula, actually. Arc length is just equal to the radius times the angle, so long as that angle is in radii, in radians. All right, this literally says a length is equal to the radius length times number of radii. So it makes quite good sense, I would say. Right. Let me next draw a circle and describe standard position. So let's say that we want to place an angle in the circle. We could place it anywhere we want, right? We could place it like this. We could place it somewhere else, like maybe over here if we wanted to. But there's a nice standard position. Okay, we place, with a C, place one ray of the angle on the positive x-axis. So, right there. And then we go either up or down depending on whether we've got a positive or negative angle. So if I've got positive angles, I go up. If I've got negative angles, I go down. So if I place an angle in standard position, that means one ray is on the positive x-axis, and then we go up if the angle is positive, down if the angle is negative. Okay, I really mean by up, I really mean counterclockwise. By down, I really mean clockwise, and this is, of course, is when viewed from the front of the page. Okay, when you've got angles in standard position and the radius of the circle is r, we have the following basic definitions. And these are called trigonometric. If you look at this, this has the nice little root of trigonal. Okay? Trigonal. What is a trigon? Well, an n-gon is some shape with n sides on it. So this is a three-sided thing, a trigonal thing. That's a triangle. Metric means measure. So trigonometric really just means we're talking about measurements of triangles. Okay? And so what triangles are we talking about? Well, for any angle in standard position, you've got a height, you've got a width, and you've got a hypotenuse length. Looks like a triangle to me. So these are trigonal measurement definitions. And here they are. We just call the ratio of the height of that triangle to the hypotenuse length the sine. So the sine of the angle is just the ratio of the height of the triangle by the radius of the circle, or the hypotenuse of the angle. Cosine of the angle is the width of that divided by the hypotenuse. Tangent is the ratio of the height to the width. And then you've got the reciprocal identities. So these are the basic three. And then we take the reciprocals and we get another basic three. We've got cosecant. That's equal to the ratio of the radius over the height. You've got secant. Oops, I forgot to draw my angle for tangent. Okay. Secant is the reciprocal of cosine, so that's r over x. And cotangent is x over y. So again, when we've got this circle, we put an angle in standard position. Here's theta. Then we have a triangle that appears. We've got some height for that triangle y. We've got some width for that triangle x. And we've got, of course, the radius of the circle, which is r. Okay, and these functions all have abbreviations. Nobody writes these out entirely like I've just done. You just write them out the very first time you've seen them, or if you're writing in sentences, you might write them out fully, but these all have abbreviations, which I'll write now. So this is sine of theta, this is tangent of theta, this is secant of theta, this is cosine of theta, this is cosecant of theta, and this is cotangent of theta. Those are the abbreviations for them. Okay. Now, we're going to shortly talk about inverses to these functions, which gets hairy, because these things fail the horizontal line test, something fierce. But before I get there, I want to just say this. So this is a way of thinking about trig functions in terms of inputs and outputs. So trig functions take input, and they give out an output. The input are angles, and they send them over to ratios of lengths, triangle lengths. Okay, you give a trig function an angle and it gives you a ratio of triangle side lengths. So this is an interpretation of the inputs and an interpretation of the outputs, right? So when we think about inverses here in a little bit, things are going to reverse. For me, it sometimes helps to remember what an interpretation is for these things so that we can sort of keep straight what's what. Okay? That'll help us keep track of inverses and functions, etc., etc. All right, so let's graph some of these things. I can't say enough that excuse me, can't say enough that graphing these things requires quite a lot of understanding of where these angles are in a circle and having a good knowledge of sort of the basics. So here are the most common angles we're going to work with. We're going to have an angle of 0. We're going to have an angle of pi over 6, have an angle of pi over 4, an angle of pi over 3, and an angle of pi over 2. Okay. And we're also going to work these in reverse. Okay. And I'm just going to write out quite a few of these. So our goal next is to be able to graph these things, but we're not going to be able to do that unless we know a table of values for them. So here's a table of values for all of them. I hope that is okay. You should be able to do this and just have it memorized, and if you don't yet, that's okay. Take this table and make it your own. I don't expect that you just have it right now, but you definitely should have this ready at some point. All right. When you're doing these, draw a circle. Draw a circle and put the angle in there every time and then figure it out, okay? So we'll remember a couple of angles here just to start off with, and these are all in standard position. So pi over 2 is this angle up here at the top. Pi is the angle all the way to the left. 3 pi over 2 is an angle down here at the bottom. And this angle here on the right is either 0, starting there, or 2 pi. All right, and then pi over 4 is right here. You can imagine taking half that top, or that top part of the circle, that's half of the total circle, and dividing into fourths. We've got pi over 4, 2 pi over 4, which is pi over 2, and 3 pi over 4. And then we've also got the fourths down below, 5 pi over 4, 6 pi over 4, and 7 pi over 4. You can also take the top and split it into thirds, which puts us right about here, and right about here for pi over 3, and 2 pi over 3. You can also take the top and split it into sixths, which puts us right about there-ish, right about here-ish. And then we've got the thirds and that half, which are also some of these sixths. So now we can more or less look at these angles in their correct position, more or less, and we can see some things that, maybe should help. Okay, so let's start with sine of 0. I've drawn the angle in already. Sine of 0 is equal to the height of that triangle that's created in there, which is the flat triangle, divided by the radius. Let's assume the circle is radius 1. Call it the unit circle. We'll just make all the radii 1. That way I don't have to write in the r every time. What is the height of that triangle? Well, it's 0. So sine of 0 is 0. How about cosine of 0? Cosine is the width of that triangle. Well, the width is exactly the radius, so that is exactly 1. And what is the ratio of height divided by width? For those two, that's the sine divided by the cosine. That's 0 over 1, which is, that's 0, right? All right, and now we can start taking reciprocals. What is the cosecant? That's the reciprocal of sine. Well, when you plug in 0 to that, you get 1 over 0, which is undefined. Secant, it's a reciprocal of cosine. So 1 over 1 is 1. I wrote tangent. I should have written cotangent. What is the cotangent of 0? That's the reciprocal of that 0, which is 1 over 0, which is undefined. And that's the table for 0, for all of them. Okay. How about an angle of pi over 6? So this is where a drawing that's really drawn to scale would really help, because if you sort of just track back, you look at this height compared to that entire height up there, it looks like it cuts it exactly in half in height, doesn't it? And that's true, it does. So an angle of pi over 6, when you go up pi over 6 radians around the circle in standard position, you actually already reach half the total height of the circle. Okay, so you don't have to go halfway through the angle to achieve half the total height of the circle. So the sine of an angle of pi over 6 is exactly half the height of that circle. That's what I'm saying right now. Okay. Cosine is, if you work out the Pythagorean theorem, you've got 1/2 squared plus the cosine squared equal to the radius squared. If it's 1, you can solve this and you'll achieve square root of 3 over 2. Okay, tangent then is the ratio of these two, sine over cosine. So 1/2 divided by square root of 3 over 2. This is 1 over root 3, which is root 3 over 3. Okay. Cosecant, we'll start taking reciprocals. The cosecant of an angle of pi over 6. It's 1 over sine, so this is 2. Secant is 1 over cosine. This is 2 over root 3, which is 2 root 3 over 3. Cotangent is the reciprocal of root 3 over 3, but that was 1 over root 3, which makes this root 3. So that's the table for those. Okay, pi over 4. Pi over 4 is the angle in here which actually forms a, if you remember this, 45, 45, 90 triangle. So we've got a 45, 45, 90 triangle in here, which means the side lengths are equal. We've got an isosceles triangle in here. And the way you can achieve equal side lengths and have radius 1 is to simply use square root of 2 over 2. So 1 over root 2 right? So we've got here that sine and cosine are going to be equal. They're both square root of 2 over 2. That's a way of writing 1 divided by root 2. Without radicals in the denominator. When you take the ratio of these two, you of course get a ratio of 1. Excuse me. Cosecant is the reciprocal of these. And secant is the reciprocal of these two up above. So we've got root 2 for both of those. And cotangent is the reciprocal of 1. That's trivial. That's easy. Sine of pi over 3. Next. There's a nice little symmetry built into the circle here, because where you have an angle of pi over 3 here, you have an angle, so this is pi over 3, you have an angle of pi over 6 here, which means the height and the width of the pi over 6 triangle can be used as the width and height of the pi over 3 triangle. Again, the pi over 3 angle here forces a pi over 6 angle there, which means you can swap the height and width of the pi over 3 and pi over 6. So if the sine of pi over 3 is equal to the cosine of pi over 6. The cosine of pi over 3 is equal to the sine of pi over 6. And because height and width have been swapped, the reciprocal of the tangent of pi over 6 is the same as the tangent of pi over 3. And then we just go through and start taking reciprocals again. Or we can think of this as swapping certain angle measurements from the pi over 6. So where are we? We've got this, root 3 over 2, which is 2 root 3 over 3. And here we've got 2, and there root 3 over 3. Okay? And then pi over 2. Pi over 2, I'm just going to make this quick. We're up here, which means the height is maxed out at the radius. The width is 0. The tangent is 1 over 0, which is undefined. And we've got cosecant, which is cosine. We've got secant, which is the reciprocal of cosine, which is undefined here because of the 0. And we've got cotangent, which is the reciprocal of undefined, which in this case is 0. Okay. So that's if you go through the angles in the first quadrant. Now, going through angles in the second quadrant or in the third quadrant or in the fourth quadrant, you're doing the exact same thing you just did, but you just need to add in signs as necessary because of just the symmetries that exist here. So pi over 6, if we go down, we're going to have the exact same height and the exact same width. So I'm just going to fill these in, the exact same, 1/2 root 3 over 2, root 3 over 3, 2 root 3 over 3, and root 3. But now we need to give them the correct signs, either positive or negative. Okay, we went below the x-axis, so the height is negative. We are still to the right of the origin, so cosine is positive. Tangent is now negative because one of those two up above was negative. Cosecant is negative because the sine is negative. Secant is positive because the cosine is positive. Cotangent is negative because the tangent was negative. So you can literally just fill in all of these same values from the right-hand side with appropriate negative signs. So I'm not going to fill that out, but that's how you would fill this out. These are the most important angles that you should remember and try to commit to memory. And really, if you know the Pythagorean theorem and you forget 2/3 of these measurements, that's okay. So long as you know the Pythagorean theorem, you can find the rest. Yikes. So with that, let's see if we can graph sine, cosine, and just take a look at that. Okay? So sine. Sine never goes higher than 1. It never goes lower than -1. Not unless we've multiplied it by a scale factor. So that height we call the amplitude. All right, sine looks like this. At an angle of 0, sine was at 0. At an angle of pi over 2, sine was at its maximum of 1. At an angle of pi, sine is back down at 0. At an angle of 3 pi over 2, sine is at its minimum at -1. And at an angle of 2 pi, sine is back down at 0. And sine does this nice little wave. Okay, and it keeps going and does this on and 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 on, forever and forever and always. Okay, it just goes and goes and goes, which, again, for any horizontal line is not good for invertibility. But that's the graph of sine of theta. All right, cosine. Let me plot here as well. I'll put sine here as in red. I'll do cosine in blue. And then I guess I'll do tangent in green. Cosine at an angle of 0 is already at its maximum 1. At an angle of pi over 2, it's down to 0. At pi, it's down to -1. At 3 pi over 2, back here, and etc., etc. We get these right out of the table of values that we just made. Okay, and cosine does this oscillation just like sine did forever and forever. Amen. Okay, it's important to note that cosine and sine are just horizontal shifts of one another. If you just shift cosine a little bit to the right, or sine a little bit to the left, or a little more to the right, whatever, they are the exact same curve. That's because of the repetition of the widths and heights and the sort of following the leader effect that happens in that circle. All right. So there's sine and cosine. Next, for tangent. Tangent is a little bit wonkier. I like to first go through and put these undefined locations for tangent. So these undefined locations for tangents, so we've got one at pi over 2. We've got one at -pi over 2. We're going to have them at odd multiples of pi over 2, actually. So 1, 3, etc. These are actually asymptotes. So for tangent, I like to put these in first. Just put little vertical bars. So there's pi over 2. Notice what happened there. Cosine was 0. Everywhere cosine is 0, you're going to have one of these asymptotes, because tangent's by definition, the ratio of the height divided by width, and cosine is literally the width. So whenever you've got division by that width of 0, you've got this asymptotic behavior. And tangent literally just does one of these things. Okay? And it does this in every single interval. Starts in the middle at 0, goes up and to the right and down and to the left, and it repeats in every single subinterval between the asymptotes over and over and over again. Okay? Where does it take a height of 1? It takes a height of 1 at exactly pi over 4. So I suppose I'm a little bit off in my drawing here. It looks like it was there. So I'll label that pi over 4, but it's a little bit off center. It should be a little to the left. So this is not a careful drawing. All right. So next, I'll describe something that we see here. We see that these are all repeating graphs. They just repeat over and over and over again. They do the exact same thing. They just repeat. We call this effect, or call this property, periodic. It's the exact same periodic for the chemistry table. Chemistry table of the elements is called the periodic table because there are periods, there are things that repeat over and over in that table. So sine and cosine are that to the 20,000th degree. We've got a period, which is repeated over and over again. Okay, so a function is periodic if there is a positive number such that if you add that amount to the input, you get the exact same thing as if you had not added that amount to the input for every x. It doesn't matter which x you pick. Okay? So it's periodic if there is a positive number p such that the input adjusted by that amount p is the same in the output as not adjusting the input. And the smallest of the values of p is called the period. So a function is periodic if there's a positive number, blah, blah. The smallest of those positive p-values is called the period. What does this look like graphically? Well, I see up here for tangent, for example, that I could pick two of these branches. I could say this right here is what I'm looking at. It looks like that's repeated over and over and over again. And I'm right. I can take this and slide it over a couple windows and it just lines right up over itself. I could even say, hey, these three are the portion that repeat over and over and over again. You take these three, you slide it over three, you slide it over three again, and you just keep going, right? I can take any number of them adjacent to one another and say, this is the repeating portion. This is the periodic part. I'm not wrong, but I could only just pick 1, 2. And so the width of one of those is what we call the period. It's the smallest number of repeating portions in the input value. So we've got for tangent, the period is from negative pi over 2 to pi over 2. That's a total width of pi. So tangent has a period of pi. I could say 2 pi, I could say 3 pi, but those are not the smallest repeating portion. Pi is the smallest repeating portion. For cosine and sine, you can look at the graph and you can determine their period. We'll do one of them. For sine here, maybe we'll select this portion here. That part of the wave is repeated over and over and over again. Starting at 0, going up to 1, down to 0, down to -1, and back up to 0. That portion is repeated over and over again, and the width of that is exactly 2 pi. Since cosine is the exact same, just slid over a little bit, horizontally shifted, we know that it is also a period 2 pi. Okay. All right, so sine and cosine have normal period 2 pi, tangent pi, and we could do the same sort of analysis for the other 3 reciprocal functions. But we don't often work with just these normal normal basic things. We often work with functions which have been transformed in some way or another. And so let me talk to you about transformations of these things and how that affects periods and things like that. So again, transformations of functions has to deal with multiplying the function's output by some number, multiplying the function's input by some number, adding some number to the function's input, adding some number to the function's output. So I'll give you a nice little description of everything that comes in this little drawing. And that's what I said, just not in words. So this times a is the multiplying of the function's output by some number. This has the effect of vertically stretching or compressing, depending on the value of that a. If it's bigger than 1, it stretches. If it's between 0 and 1, it compresses. If it's negative, it flips vertically about the x-axis. Another thing that affects this vertically is this d. This is a vertical shift. It lifts the whole graph up. It lifts the whole graph down if it's negative. Just adding a number to the function's output has the effect of pushing something up or down on the plane. Okay? When you're dealing with outputs, you're dealing with vertical amounts. You're dealing with heights. When you deal with inputs, you deal with left and right. So this plus c shifts horizontally. Okay. If you're adding some number there, you're actually shifting to the left. If you're subtracting there, you're actually shifting to the right. B here has the effect that we had with the multiplication outside the function. This stretches or compresses stretches or compresses as well. Okay. So what does this mean for something like a trig function? Well, the way that this is written is very suggestive of trig functions. Okay. So if I say y equals 2 sine of 3 pi x minus pi over 2 plus 3. What does that look like, or what happened to the sine function? Well, this is the sine function, but it's twice as tall. Okay, so instead of going up to 1 and down to -1, it would instead, if forgetting this thing on the right for a minute, it would instead go up 2 and down 2 from equilibrium. This 3 on the right means we've lifted the whole graph up 3 units. So if I wanted to graph this already, I would know 1, 2, 3, that this horizontal line at y equals 3 is our new equilibrium point, and that our graph is going to go up 2 to 5 and down to 1 because of that 2 and because of that 3. I know these things already. Okay, next, I know this pi over 2 has the effect of horizontally shifting the sine graph. So before, when it started at 0, 0, and started doing this, now I know it's going to be shifted to the right, pi over 2. So this 0 point is now starting at pi over 2, and then it was going to start doing something like that. But that's the new starting point. So pi over 2. It's going to start right there. And then what about this 3 pi? So whenever you've got a trig function where you've got a some multiple of the x. Okay, so if you distribute this through 3 pi times x, the new period is going to equal 2 pi divided by whatever that value is. So I'm going to write a little b because that's what we used up here. So if you can write your trig function like this, b times the quantity x plus c. If you take 2 pi for sine and cosine, divide it by that number b, you get the new period. The new period, okay? You take the old period divided by that number b to get the new period. So for tangent, it would be pi divided by b. But for sine and cosine, it's 2 pi over b. So what's the new period for us? So that's 3 pi over 2 pi, which is 3/2. The new period is 3/2. So pi over 2, and I'm just making this up now. I don't know exactly how far over this should be. Pi over 2 plus 3/2, that's the end of one period. That means the entire wave is going to fit between those 2 points. One entire wave. So I'm going to go up to 5, back down in the middle, down to 1, and then back up there. And if I do a half decent job at that, it'll actually look believable. Okay? And there, we've plotted what we call one wavelength, one period of the curve. And we can just keep going. Oops, that was the eraser. And we can just keep going if we wanted to. Sometimes I'll ask you to plot 1 period or 2 periods. For now, I'm just plotting the 1. All right, again, just to reiterate, this plus 3 is what brought our middle line, our equilibrium point, up. Okay? This minus 2 is what brought our original point, minus pi over 2 is what brought our starting point, pi over 2 to the right. Okay. This 2 is what increased our maximum height from 1 up to 2. And this maximum height is around that equilibrium line. So from 1 to 5 is 2, and from 3 to 1 is also 2. So we see that height here, we see that height here. That's often called the amplitude. This 3 pi is what affected our period. Normally sine goes from 0 to 2 pi for one full wavelength, but this one is oscillating much more quickly. It goes through its period 3 pi times faster than it did before. Okay, so it has only a period of 3/2, which is about 1.5, not a period of about 6 1/4. Okay, so approximately 4, almost 4 and a bit fit into the original period. Okay, this very same reasoning of shifting left-right, stretching left-right, stretching vertically, shifting vertically, you can apply the exact same reasoning to plotting any sinusoidal function, really any function, period. All right, the last thing for this lesson, I know this is a long one here, is talking about inverse trig functions. So let me first just talk about the necessity for a piece of this. You can invert any old function, right? We just had this last lesson. You can invert any old function, but you're not guaranteed a function inverse, a functional inverse, unless the function is 1-to-1. Trig functions are not even close to 1-to-1. They just aren't. I would think of the graph for any of them. Here's sine or cosine. If I draw one horizontal line, how many points does it hit? It hits an infinite number of points. So if you give me that height, let's say this corresponded to a ratio of y equals 1/2, what would the sine inverse of 1/2 be? What would be an infinite list? Of values. Every single angle with height 1/2. Okay, so that makes this inverse a relation, not a function. So one thing that is commonly done with functions that are not one-to-one is you restrict their domain to a portion that is invertible, and then everybody shakes hands and says, this is what we mean when we're talking about the function and its inverse. And so that's what's done with cosine, sine, tangent, everything. There's an agreement that we are going to use only a portion of their domain, and we're all going to agree upon that portion, and that's going to be fine. The world will work out much better because the functions will have functional inverses. So here we go. I'll just write down a table of these things. So cosine of an angle, right? Cosine usually has domain anything, and its range is -1 to 1. Cosine inverse, okay, well, its domain is going to be the range that we had before. Remember that we swap x and y's when we're finding algebraically a function's inverse. That literally means to swap domain and range. So the cosine inverse's domain is the range that we had before. But we need to restrict what we can get out, which means we need to restrict the previous domain so that we don't get an infinite list. And so that's where this comes in. So for cosine, we only allow for the output to be between 0 and pi. So if I ever ask you what's the cosine inverse of root 3 over 2, don't you dare give me an angle outside of 0 to pi. That's what that means. Okay? So I'm not going to write out the sine and tangent, things like this. That was for illustration here with cosine to get the whole ball rolling. I'm going to keep going now with sine and the others. So sine inverse has domain the same, -1 to 1. Range, not the same. Oh, wouldn't it be great if we could all just agree on something that's nice? There it is, -pi/2 to pi/2. This is not because we couldn't agree on something that's nice. This has to deal with what the functions are themselves. If we go back to their graphs, I'll draw you a picture in a bit. Tangent inverse has domain of anything, literally anything. Okay, you think about tangent and how the outputs of tangent can be any real number. That means the domain of its inverse can be any real number. And you think about the domain of tangent, and that becomes the range here, right? So for tangent, we've got this. We remember the asymptotes at pi/2 and -pi/2, so I've left them out of this range. Okay. All right. Secant, cosecant. So these things are a little bit stranger. So the domain of these things are, any angle whose absolute value is greater than 1. For cotangent, it's anything. Back to secant and cosecant. Right, so secant, we've got anything between 0 and pi. But I'm going to take out, that's what this slash means, take out pi over 2. Okay, another way of writing that is 0 to pi over 2 together with pi over 2 to pi. Right? Then for cosecant, we have another something strange. The range is negative pi over 2 to pi over 2, except for 0. And then for cotangent inverse, the range is 0 to pi, not including the endpoints. And so where do these strange domains come in? Where do these strange ranges come in? Why 0 to pi? Why negative pi over 2 to pi over 2? It all goes back to the graphs of these things. I think that's a nice way to think about it. So sine oscillates back and forth, back and forth. Here's a nice little graph of it. We need a 1-to-1 portion. Cosine used 0 to pi. So let's plot that out. Here's sine from 0 to pi. That's sine from 0 to pi. That's not 1-to-1. So for sine, we restrict to this piece of it. From negative pi over 2 to pi over 2, because that's a 1-to-1 portion of sine. So when we're taking inverses, we're going to take whichever point along this little bar that has the height we're looking for. Okay, that's why tangent inverse and cosine inverse also have their sort of strange intervals, if you will, because we're looking for a portion that is 1-to-1. And secant and cosecant inverse, that's why their domains and ranges are quite weird, because if you plot them and you look for a 1-to-1 portion, you're going to have to make some decisions about what portions you choose. Okay? And that's it. That is inverses for trig functions, and that is trig functions. That was a really long lesson. If you made it to the end, you must be taking legal stimulants and drinking lots of caffeine. So, well done. Right. Okay, well, hopefully that's good enough. Please let me know if you have questions.